Uh, Today we will solve the problem 2.49 of Griffith 4th edition, Introduction to Electrodynamics. The problem 2.49 is a sphere of radius r carries a charge density rho of r, which is equal to kr, where k is a constant. Find the energy of the configuration. Check your answer by calculating it in at least two different ways. So, first you take the Gauss theorem, that is closed integral of E dot dA is equal to the charge enclosed in the Gaussian surface over epsilon naught. So here is given is the sphere of radius r. This radius is r, and we are taking the point inside the sphere. We can take inside as well as outside. Inside this point, which is r prime, which we call it as r prime. After all, this is a running index. You can keep it as r prime or r double prime, whatever may be. So now your task is you have to find the charge enclosed over epsilon naught. Uh, that is charge enclosed over epsilon naught is equal to 1 over epsilon naught. I am taking epsilon naught outside is a constant, and here volume density is given as rho. So you have to integrate rho over the enclosed volume. Rho t tau. T tau is the volume, small volume, which is equal to, in our case, we have taken this as r prime squared sine theta t theta uh, t pi t r prime. So this is the triple integral. So what is rho? Rho, in our case, we have taken that point as r prime. So this is k r prime. So you substitute this in the place of tau. Then you take k outside. Already one constant is outside. K over epsilon naught. This r prime and this r prime squared will become r prime cube. You are integrating with respect to t r prime. Then you integrate this 0 to pi sine theta t theta and 0 to 2 pi t pi. So third one is a very simple, is a standard integral for which the value is 2 pi. So we got 2 pi. Uh, then what about the sine theta t theta? If you integrate sine theta, you will get minus cos theta. And you have to apply the limit to 0 to pi. So you take negative sign outside, then apply upper limit cos pi minus cos 0, lower limit. So minus cos pi is minus 1, cos 0 is 1, minus 1 is equal to minus 2, there is 1 minus outside, so this will be 2. So I have taken 2. Then you come to this r integral. So if you integrate this r prime cube, you will get r prime power 4 divided by 4. So here you have to apply the limit 0 to r, remember that, 0 to r. Then you can cancel this 4 with this 2 into 2, 4. So if you apply the limit r, maximum limit, minimum limit is 0, so don't worry about it. Maximum limit, this r prime 4 will become r power 4. There is pi here. So pi k r power 4 divided by epsilon naught. So Q enclosed inside the sphere where r prime is less than r. So this is inside. Remember that this is inside. Similarly, we have to calculate the outside. We have seen the ratio of Q enclosed to epsilon naught as pi k r power 4 over epsilon naught. This is inside the sphere. Remember that I want to trust this point. This is inside the sphere. Then we have to calculate the electric field inside the sphere. So closed integral E dot dA is equal to Q enclosed over epsilon naught. So we have calculated right hand side as pi k r power 4 over epsilon naught, and you take left hand side. Left hand side TA is equal to that is area enclosed is 4 pi r squared. So E dot 4 pi r squared is equal to pi k r power 4 over epsilon naught. Here you can cancel some of the things. That is, you can cancel pi and this pi, and you can cancel this r squared with this r power 4, which will become r squared. So in the numerator you have r squared, kr square, in fact kr squared over epsilon naught. You bring this 4 to the other side, you will get 4 epsilon naught. So the electric field inside is kr squared over 4 epsilon naught. So this is inside. Remember that I have mentioned sub sub inside. So similarly for outside, outside is see, you take this r outside the point. This is the radius, and you are taking r outside. So here in this case r is greater than capital R, that is outside. So Q enclosed, ratio between the Q enclosed over epsilon naught for outside, this is for outside, is equal to, you take 1 over epsilon naught outside, same integral rho t tau. T tau you do whatever you have done in earlier case. Then you know this integral is 2 pi, sorry 2. The third integral is 2 pi. Exactly the same method. This will become r power 4 over 4. Exactly the same thing. Only thing is this limit is capital R, not small r, because we are considering the entire sphere. Because it is outside, you have to take the entire charge. That is charge inside the sphere, entire sphere. So the limit is not r, small r here. It's capital R. Sorry, here I have to use capital R, capital RQ. This is a capital R power 4. If you multiply 3, here you have k by epsilon naught. So k by epsilon naught, sorry, k pi epsilon naught. K by epsilon naught. Then here you have r power 4 over 4. These two into 2 pi, 4 pi, you will get 4 pi. Here 4 will get cancelled. So you will get pi krq over epsilon naught. This is the final answer for outside. This is outside. So electric field outside, you take this expression. Electric field outside is, here area is 4 pi r squared, which is equal to pi k r power 4 epsilon naught. Here also, as we have done earlier, you cancel this pi. But here it is small r, this side is capital R, you cannot cancel. So the electric field outside is k r power 4 divided by, you bring this 4 r squared here. So you will get 4 epsilon naught r squared. So 4 epsilon naught r squared. We will reduce it further. We will expand this further, sorry. So we have calculated the electric field inside and outside. Now we have to calculate the energy, that is work done, which is equal to epsilon naught over 2 integral E squared T tau. Here the work done is, is equal to half epsilon naught T square. So we have taken the E squared for the entire volume. That is why we have taken a E squared for a small volume element, and if you integrate, you will get for total sphere. So here this E can be separated into two parts. One is inside the sphere, that is inside the sphere, which I have written as E sub in square, and the t tau is equal to 4 pi r squared tr. So 4 pi r squared area into the thickness, that is small element tr is will give you the volume. This is t tau, area into thickness of the selected portion, plus the E outside. So E outside, same thing, 4 pi r square tr is t tau. This is E inside means it is between 0 to capital R. Outside means from capital R to infinite. That limit also you have to take. We have seen E in is equal to this terms inside the bracket, that is k r squared over 4 epsilon naught. Then you have to square this. Similarly, E out is this one, the terms inside the bracket, that is k r power 4 over 4 epsilon naught r squared whole squared, and you have that usual 4 pi squared 4 pi r squared tr, 4 pi r squared tr. Now what I can do is I can cancel this 2 with this 4, you will get 2. So the first integral will become 2 pi, I am taking out 2 pi epsilon naught, and here constants are k over 4 epsilon naught. So k by 4 epsilon naught whole squared, I have taken that constant also out. So here the running index is r squared up squared, r power 4. Here we have one r squared. Pi I have taken already out. So r power 4 into r squared is r power 6 tr. Similarly, you come to second integral. Second integral also you will get this 2 will get cancelled with this 4, you will get to 2 pi. You take 2 pi outside. So 2 pi epsilon naught. Here constants are k r squared over 4 epsilon naught whole squared. So you leave 1 over r squared here. R square of square is r power 4. So this is 1 over r power 4, and already we have r squared outside. So both will get cancelled, it will become r squared, 1 over r squared. So I have taken k r power 4 over 4 epsilon naught whole square, integral between r to infinite, that is outside the sphere, 1 over r squared tr. Now we can square it, that is it will become k squared. Of course you have taken 2 pi epsilon naught as it is. This will become k squared, 4 squared is 16, and epsilon naught squared. So epsilon naught square is epsilon naught square. Similarly, if you integrate this, you will get r power 7 over 7, and you have to apply the limit to 0 to r. Same thing, second integral, 2 pi epsilon naught, you square it. K squared r power 8 divided by 16 epsilon naught squared. So you have epsilon naught squared, and if you integrate this, you will get minus 1 over r, between the limit, lower limit is r, upper limit is infinite. So we will do the calculation further. Now we got this result, that is work done is equal to 2 pi epsilon naught k squared over 16 epsilon naught squared, r power 7 over 7 between the limit 0 to r, Same thing, 2 pi epsilon naught k squared r power 8 over 16 epsilon naught square. This minus 1 over r between the limit r to infinite. So now you can cancel some of the term. Uh, 2 will cancel with this 16, will become 8. This epsilon naught will get cancelled with the epsilon naught squared. This will simply become epsilon naught. Same thing here. 2 is 16 will become 8. This epsilon will get cancelled this square. The first term is pi. Here you have pi k squared over 8 epsilon naught. Then after applying the limit, this will become r power 7 over 7. Then here you come here, you have pi k squared r power 8 over 8 epsilon naught. Here you apply the upper limit. 1 over infinite is 0. Then 1 over r, remember that there is a minus. 1 over r is, first term is 1 over infinite 0, minus 1 over r is 1 over r. So minus of minus will become plus. So this will become simply plus 1 over r. Here you can cancel this r with this r power 8, which will become r power 7. So here you can see pi k squared r power 7 over 8 epsilon naught is a constant. I am taking that out. So in the first term you have 1 over 7. In the second term it is simply 1. So if you take 7 as LCM, you will get 1 plus 7, which is equal to 8 by 7. This bracket term will become 8 by 7. This 8 and this 8 will get cancelled. So you will get pi k squared r power 7 over 7 epsilon naught. This is the answer. We have solved it using one method. We will go for another method in the next lecture. Thank you very much for watching my video and supporting me continuously. Thank you very much.